Hello all, welcome to this course on computer organization. The topics we'll be seeing today are single cycle data path for R-type instructions including BEQ. BEQ stands for branch when equal, single cycle control and its performance analysis. Now let's get started. First we'll see the single cycle data path for R-type instruction including BEQ. So we go on with this designing with an assumption that you are already familiar with the data path for an R-type instruction, and if you are not, I would request you to kindly go through my previous video on the same so you'll have a better idea on what we are doing here. So what is BEQ? BEQ, as I said, is branch when equal, and it's an example of a conditional branch that's used in MIPS. And this is the format: BEQ followed by two source registers RS, RT and an immediate value. What does this BEQ do? It compares two registers. If they are equal, it takes the branch by adding the branch offset to your program counter value. Now, what's this offset? It is a positive or negative value that's stored in the immediate field of the instruction bits 0 to 15. Now, what does this offset indicate? It stands for the number of instructions to branch past. That is the number of instructions you need to skip. So you'll see this example over here. It's a MIPS assembly code that states how BEQ works. So here you can see that we are comparing the value of two registers $S0 and $S1. Any register that precedes with a $S is called a saved variable in the MIPS register set. So you can see that the values of these two are equal, so it will take into consideration this offset. And this will contain to which location you need to branch out. So later in the program, you can see the same label target followed by a colon. So if these values are the same, control is transferred to this instruction and these two are purposefully skipped out. So that is said here, if equal, the branch is taken. Now, so how do you get the new program counter value? You will sign extend this immediate value. Why do you do that? Because you need to accommodate both positive and negative values, and also you will multiply this by 4 in order to get the new PC dash. Why? How do you normally get the new PC dash value? PC plus 4. And why 4? We assume throughout these videos that we are considering MIPS with 32-bit architecture. How many bytes are there in 32-bit? We have 4 bytes. So since MIPS is a byte addressable memory, that is, each byte will have a unique address, you give the number of bytes that you need to add to the current location in order to get the new location. That's why you give here a 4. Similarly, the sign immediate will tell you the number of instructions you need to skip, not the number of bytes. So what you do? You multiply that value by 4. So when you see the right hand side of this equation, you can understand that you'll get the total number of bytes that you need to add to the current value of PC so that you get the new value of PC dash. Now, with these ideas, let's go to the designing part. Here, these blue lines, they stand for the new control signals you're adding into this. And these black lines, they stand for the extra hardware you're adding here. So, here, the next PC value is taken from here. The next PC value for a taken branch, that is if the registers are equal, we call it as PC branch. This value, it is computed by shifting the sign immediate to the left by 2 bits and then adding it to PC plus 4. This value, originally it went through this side, you're extending it to the other side also. So, why do you do a left shift by 2? Because it's an easy way to multiply by 4, because a shift by a constant amount involves just wires. Next, you need to compare those two registers and you do it by computing SRCA minus SRCB using the ALU. If your ALU result is 0, as indicated by the 0 flag from the ALU, that means your registers are equal. Now, we'll add a multiplexer here to choose PC dash from either PC plus 4 or the PC branch here. So this PC branch is selected if your instruction is a branch and the 0 flag is asserted here. Hence, the branch is 1 for BEQ and 0 for other instructions. Also for BEQ, the ALU control value will be 110. Here you will see in this truth table that for 110 they do an A minus B. That's why you have this value here. So it performs subtraction and ALU SRC will be 0. Why? Because you need to choose this SRCB from the register file. And also you will see that the register write and mem write values are 0. Why? Because the branch does not write to register file or the memory. We also don't care about the values of regdst and mem to reg because the register file is not written. So this multiplexer have this as the select line PC source, and the value of PC source is got by ANDing the value of the 0 flag and the branch value. Okay, so that's all for the designing part. Now we'll see about single cycle control. So on going through the previous designing, it can look quite confusing that you have so many control lines here, you don't have a common source. And we always discuss about control units in computers, right? So they are necessarily giving the control signals to different parts. So in single cycle control, we are planning to replace this design with a central control unit so that you have all these control signals originating from this control unit. So how do you do that? What does a control unit do here? This control unit, they compute the control signals based on the opcode and func fields of the instruction, that is bits 26 to 31 and bits 0 to 5 here. Since we are discussing an R-type instruction, this is the format followed. We were talking about this one, 26 to 31 bits and func field 0 to 5 bits. So most control information, they come from the opcode. But R-type instruction also use a func field to determine ALU operation. When you look into the format of an I-type or a J-type instruction, you will see that you just have an opcode here. You don't have a function field. But in R-type, you will have this. They give in additional input to which ALU operation is to be performed. Also, we are trying to simplify this design we derived before. How? By adding a control unit and dividing it into two blocks of combinational logic. So you have a main decoder that compute most of the outputs from the opcode value. That's bits, these bits 0 to 5. Okay, it also determines an ALU OP signal, a 2-bit signal. You can see the truth table here. If both the bits are 0, it stands for addition. If it's 0, 1, stands for subtraction. If it's 1, 0, it further looks into the func field to decide which ALU operation is to be performed, and if it's 1, 1, it's not applicable. And you have an ALU decoder which takes this ALU OP as input, and also it uses the func field to compute what your ALU control, the 3-bit value, this one. Okay, so yeah, this way, yes, you have replaced this architecture, this one, you insert the control unit here. So the entire thing is your control unit. Inside the control unit, you have 2 divisions, that's all. But you insert it as a single unit. Also, you'll see that since your ALUOP value is never 1, 1, your truth table can use don't care values, right? We'll see here, we have ALU decoder and main decoder. You have derived the truth tables for both of them. So it's never 1, 1, so you insert x1 and 1x instead of 0, 1 and 1, 0 to simplify the logic. So when your ALU OP is 0, 0 or 0, 1, here it's x1. That means your ALU should do an addition or subtraction respectively. And the value of ALU OP is 10. That's given as 1x here. Your decoder examines the function field also to determine the ALU control. Also note that for R-type instruction, we implement the first two bits of the funct field as 1, 0, and so that you can ignore it to simplify your decoder. All the R-type instructions use the same main decoder truth table values, and they only differ in the ALU decoder output. Also recall for instructions that do not write to register file, like your store and your BEQ. Here the value of regdst and the value of mem to reg control signals are don't cares. The address and the data to register write ports, they don't matter. Why? Because reg write is not asserted during this process. So this is how it looks. You have the opcode field 26 to 31 and this is your funct field. Your control unit as given here, you have mem to reg, mem write, branch, ALU, SRC, reg DST and reg write here. All of them like this, and here also like we did for BEQ, you have an and you give it to this multiplex. So that is how you complete the design for that. Next, we look into the performance analysis of single cycle data path. So what was the characteristic feature of this single cycle data path? Here, each instruction in the single cycle processor, they take only one clock cycle. So the cycles per instruction or CPI value will be 1. So we are discussing how do we calculate the performance using the example of a load instruction, and we are trying to derive the critical path here. Okay, what is this critical path? The critical path is defined as the path between your input and output with maximum propagation delay. So in the first video I uploaded regarding the performance analysis of MIPS, we discussed that we usually do it by calculating the total execution time. So total execution time is the values, number of instructions multiplied by cycles per instruction multiplied by the seconds per cycle. Here cycles per instruction will be 1. Number of instruction depends on your program, and the seconds per cycle, that actually depends upon the critical path. That is why we drew the design for the load instruction and we are trying to mark the critical path involved here. We did it using dashed blue lines here. So it starts with the PC loading a new address during the rising edge of the clock. And we also discussed that this architecture, it always is in rising edge of the clock that the state elements change their state. That is why we specify the rising edge here. So that is why it's also called sequential synchronous circuits. Okay, and the instruction memory here, instruction memory reads the next instruction and the register file reads SRC-A. While the register file is reading, the immediate field is sign extended and selected at ALU SRC here. Multiplexer to determine SRC-B, and ALU adds SRC-A and SRC-B to find the effective address. And the data memory reads from this address, and the mem to reg, this control line here. Multiplexer selects read data. Finally, the result must set up at register file here before the next rising clock edge so that it can be properly written. So hence you can say that the cycle time here is given by TPCQ dash PC plus tmem plus max of trf read, comma tsext plus tmux plus talu plus tmem plus tmux plus trf setup. So what does all these people meant? That is here T PCQ PC. Generally it means the propagation delay involved in your PC program counter. What is PCQ? It actually stands for PCQ is register clock to queue. The queue, there can be the output of a flip-flop or a register. Here we consider the register because our design involves only registers. So why do you need that value there? This our critical path involves PC, and for an edge triggered register, the time it takes for the register output to be in a stable state after a clock edge occur is this value. That is why you are adding it to the cycle time here, because we already learned that any transition happens during the rising edge of the clock, so that it should be the adequate time so that your register has a stable state. It should not be having two values at the same time. That's what this time stands for. Then this tmem, you have two tmems here. Your critical path involves both the instruction memory and data memory. So that propagation delay is shown by these two values. Then you see that RF read is the read propagation delay in your register file. SEXT is the propagation delay for sign extend logic, and TMUX, as you know, is the propagation delay for multiplexer. So all these units are involved in your critical path, the register file, the sign extension, and also this multiplexer. So here you have given a max function and given these two values here. Why? Because this SRC-A is obtained from here and SRC-B is given through here. So whichever of them is the maximum, you add that to the critical path value. Then TALU, because you have an ALU involved here, you add the propagation delay there. Then TMEM, as you all know, we discussed it earlier, and you have another multiplexer. Yes, this guy here. Then also TRF setup. That is the setup time for your file, register file. That is the register value is written during the clock edge. That is why you need this to add this time also to the equation. When you again examine this equation, you will understand that generally in most of the implementation technologies, your ALU, your memory, and the register file accesses are substantially lower than other operations. So you can actually simplify the performance analysis as TPCQ PC plus 2 tmem plus trf read. So you ignore this, plus TALU plus tmux plus trf setup. This is for load that we have calculated. We derived this using the critical path for a load instruction. So other instructions have shorter critical paths. Like for example, we take R-type instructions. They do not need to access the data memory. So their critical paths will be much smaller. Okay, when you brief up, like, what all did we learn today? We learned how to design a single cycle data path for R-type instruction, including BEQ. So we did it here. We saw how BEQ works. And you've seen that the sign extended value, you shift it to the left by 2 bits and you add it with PC plus 4 if the branch is taken. Otherwise, the value will be PC plus 4. You add a multiplexer here, which is controlled by PC source, which is actually the value obtained by ANDing the 0 flag here and the branch value, which will be 1 for BEQ. Here the ALU control will be 110 and ALU SRC will be 0. So you take the source value SRCB. Okay. Then we saw the single cycle control. How can we replace a control unit here? So yeah, you have two fields to be taken into consideration, the opcode field and the funct field. You divided the control unit into two combinational logics, the main decoder and the ALU decoder. The opcode value decides in the main decoder to give out the signals like mem to reg, mem write branch, ALU SRC, reg DST and reg write. The output of the main decoder, that is an ALU OP, 2-bit value is given to your ALU decoder, which along with funct value decides the ALU control. So these are the truth tables. Then we replaced it actually when we saw the truth tables for these two units. You will see that 0, 0 and x1 values. Yeah, why this x1 or 1x came? Because your value can never be 1, 1. So you are replacing it with x1 or 1x. So if the ALUOP value is 0, 0 or x1, it's addition or subtraction. And when the ALUOP value is 1x, you need to add the funct field also to see which instruction is to be executed here. Also, when you see the main decoder truth table, you will see that the reg DST and mem to reg values for store and BEQ are don't cares. Why? Because they do not write to the register file. Also, the value of reg write, and that is for your store instruction and BEQ are 0 because we don't do any address or data writing to your register write port during these instruction because that doesn't matter at that time. Then we saw the performance analysis. Since it's single cycle data path, you have the cycles per instruction as 1. This is the execution, total execution time. So here the seconds per cycle depends upon the critical path. That is why you're considering the critical path here for load instruction. We have taken the example of a load to derive the cycle time. How do you derive the cycle time? You take into consideration the propagation delay involved in all the units here, which lie along the critical path. And you saw that the time taken by ALU, memory, and your register files were much slower. So you add those units, this also program counter. So you take into consideration those units and you derive your cycle time for single cycle data path. So that's all. Thank you all. Thank you for listening.